kind of briefly what our topics are for the day. Uh, we're going to talk about water quality modeling basics, and we're not going to be able to hit everything because this is a really big topic. So we'll just imagine that we're skipping along the surface to hit a few things, hit a few important things. Because what we're really focused on is how to use water quality modeling in WaterGEMS. And today I picked WaterGEMS. I could have picked WaterCAD Connect Edition as well. I just happened to pick WaterGEMS. We can use the same tool in both, but what we're actually going to be taking a peek at is the constituent modeling and water age modeling in WaterGEMS Connect Edition. So again, you can also do this in WaterCAD Connect Edition as well. Okay. What is water quality modeling? If you were to look at the classic definition, it would read something like simulation of physical, chemical, and biological processes, including the movement and transformation of those components through a water distribution system. Now, that is a long definition, and you can read it on the screen too. But basically, what water quality modeling is trying to do is trying to fill in the gaps from any known data that you have, any sample data points that you do have, and fill in and paint the picture of what's going on in the rest of the system, your water distribution system, because there's no way you're ever going to know exactly what every single water quality parameter is throughout the entire system. So this nice thematic graphic of chlorine residuals throughout the system. I believe the darker amount is a higher chlorine residual concentration. The lighter amount is a lower residual concentration. There's no way you would ever be able to really see what that is unless you had some type of water quality modeling, some type of computer software to help you see all of those variables. Yes, you can get a really high confidence just by measuring a value somewhere out there in the distribution system, but you need a tool to help you do that. So towards the end of this discussion, we're going to get into that tool, but I wanted to just talk a little bit real quick about water quality modeling itself and why you might want to do it. Maybe you're doing it to answer a few of these objectives. You have different sources that you're trying to mix. Maybe it's chloramine and chlorine sources. Um, and you're trying to figure out what's going to happen, how well, how much volume of one or the other you should be mixing. Same thing for total dissolved solids. Maybe you've got a well field that's got high TDS and you're not quite sure how much TDS concentration of that one well field you should bring into the rest of the collection system. Maybe you're trying to scratch your head and figure out where you should put a chlorine booster station. That's kind of a typical one you might see. Or how to reduce DBPs. You know you have DBP formation and you're trying to figure out how to reduce that and how to get the water to move through the system more quickly. And maybe this is all resulting from too much money from flushing. Or you're trying to understand taste and odor complaints. So that's also a likely one that could be going on. Maybe you're trying to determine a contamination source. So there's lots of different objectives you could be trying to achieve by trying to solve and use a water quality model. And again, there's there's a lot of things that you could be meaning when you say water quality modeling or you're concerned about water quality. And today we're really going to focus on a few of the just a few of the chemical constituents in water age. So we don't have time enough to go into all of the topics, so we're just kind of focus in on just a few. Some water quality constituents that you really might be interested in and can indeed model with WaterGEMS and WaterCAD. Maybe it's nitrates and nitrates. Maybe it's metals, and these would be lighter metals. Chlorine, chloramines, some organics, DBPs. DBP is a disinfection byproduct. Generally, these are not favorable. So you might see THMs and HAAs as an example of these acronymic soup things, disinfection byproducts. But those could be forming out in your system. At the same time, all of these non-conservative substances they are forming and changing due to some chemical and biological process. And that process is very complex. So again, in just a few slides, I'll show you how we handle that in a water quality model in WaterCAD and WaterGEMS. But let's just park that thought for a moment and say it's pretty complex because there's a lot going on, temperature, pH, and everything else. On the other side, salinity, total dissolved solids, and fluoride, these are examples of something that changes due to mixing. There's not a whole lot of reaction going on for these, but they change due to mixing. Now these behave differently, all right? One's just how things are mixing throughout the system in the tank and in the connections, and the other one on the left there, it's changing due to some reaction rate somewhere. So we've got two different types of variables to deal with. And lead, some lead constituents are pretty stable once they're bound to other chemicals. So now this approach of how things change out in the system, we're going to go just one more step deeper here. You can model these things with decay rates or growth rates. And again, we're going to skip across the surface here a little bit. Chlorine is something that would typically be decaying over time. So it would start out at some initial concentration that has been entered in at the treatment plant or something, and then it begins to decay over time exponentially to some point approaching zero. And on the other end, a constituent like a DBP, a disinfection byproduct, trihalomethanes is the example here, they are going to grow exponentially to some equilibrium, some maximum point. And the reason they hit some maximum point is their building blocks to make these have been exhausted. Maybe there's no more chlorine. So there's a behavior of the constituents, if you will, out in the water distribution system that are all being driven by temperature and pH and the other background constituents and chemicals in the water. So where we're heading is trying to digest that decay rate into something that's predictable, that we've derived from somewhere, and then we can then go into the water quality model and say, here's the behavior of that constituent. Now, how do you determine what that rate is? Well, here's an example of how you might determine it. We're going to go look at the example of chlorine. You would use, typically, you would grab 10 bottles of that source water, go store it in a dark place, and this is, say, treatment plant water, okay? Wherever your water source is coming from, and you're looking at the decay of chlorine. So grab 10 bottles. They would be nice and sealed up, no air gaps in there. Put them in a dark place, constant room temperature. And then what you're going to do is at various intervals you're going to come back over a few hours and a few days and start taking measurements of the chlorine residual in those bottles. Okay, pretty straightforward here, and you're going to be recording what time that was and what the value was. And then you'll continue to do this for the duration of the water age in your distribution system. So it could be a couple days, getting into a couple weeks. And then what you do is you end up plotting that change in chlorine over time. You plot that, and then you're able to derive what the actual K value is. And again, these are recorded, so you can always come back and kind of re-watch this and redigest the formulas here. Or you can pick up the Water Distribution Design and Modeling book. It's got a lot more detail too. But just for today, we're going to kind of zone in on the K value. That K value you would derive from laboratory work somewhere. You would get that, and that K value, you are then assuming that everything going on in the system that impacts that chlorine can be translated to that decay rate. This does get a little more complicated if you have blending of source waters, so you would then need to blend the source waters to see what that ultimate decay rate would be then too. I was going to put in a few more slides about chemical equations on here, but it probably would have gotten a little bit more deep than we need to get today. But suffice it to say, there's a lot of things going on in the background that would just be very difficult for a lot of computer systems to handle right now. Perhaps this is something in the future that we may be seeing, but for now, you would be putting in that K value. Okay, now switching gears a little bit, there's that decay rate, but then there's also when you're approaching a water model and you're setting up a water model, you have some initial value out there in the distribution system. So you're about to go model it, you're about to go collect data, and there's some value there. Like tanks actually have some concentration already. They don't start out at zero. I guess if they are zero, then that's probably why you might be caring about disinfectant residuals. But generally, the tanks have some concentration. Generally, the water in the pipes has some concentration already. So you'll have the opportunity that you'll see here in just a moment to pick initial concentrations for nodes, for tanks. Um, Make sure that you are picking something that's realistic and that makes sense, because if you don't, the thing to note here is it will take a while for the model to start reaching an equilibrium where it's repeating and actually becoming more relative to what's out in the real world. It may take a while longer for it to converge. So start out with good initial concentrations or initial conditions for a tank. That's the moral of the story here. One other, after we get into chlorine modeling with WaterGEMS, I'll also show you some modeling of water age. And just very quickly, um, water age is determined at each node. It's heavily influenced again by tanks and reservoirs. So those initial conditions of how old water is in a tank is important. So you would start off by having a general idea of how old you think water may be in a tank. It could be a week, it could be a couple weeks, something along those lines. And again, I'm going to show you where we enter this into the software and how to do that. And as you would think, age is typically highest at dead ends of a line. And again, I'll say again, consider the initial tank conditions whenever you're running a water quality model, be it water age or be it some constituent or chemical out there that you're trying to model. Okay, so that's kind of just the background again. During one of our courses, we'll go into a lot more detail on water quality modeling. There's other sources out there. AWWA, great source. Again, I'll try and be providing you some of the links towards the end of the SIG for some sources that you can go to. But for now, we're going to go ahead and start heading right into the software here. Some of the different types of modeling that we could do in WaterCAD and WaterGEMS. We can model constituents. We can model the decay of those constituents of the growth. So decay would be chlorine perhaps. Growth could be DBPs again. You can do source tracing or look at water age. So we're going to get into constituent and water age today. You would start off by going into calculation options and then selecting the type of model run that you're about to do. So you'll see a list, fire flow, we've talked about that in the past, flushing, but in this case it would be trace, constituent, or age related to water quality. So basically you would go into the calculation options in WaterCAD or WaterGEMS and tell it what type of run you're about to do. And then the next fairly important area when it comes to water quality modeling is you would go in and create a constituent. And this is where you have the opportunity to enter that K value, that value that I was mentioning earlier, where you can do a bottle test and determine the decay rate. Well, in this case, you can go in and enter the decay rate, let's say for chlorine or something, whatever you derived. And the bulk reaction rate or bulk reaction order, first order, first order would be exponential growth or decay. Zero order would be something that's growing linearly. One of the few things that might be growing linearly in a system would be time, water age. But in this case, chlorine, you could go in and have the ability to enter in the decay rate and also set the wall reaction rate. And this might be a whole nother area to talk about again. But wall reaction rates are real. Things do happen at the wall chemically. Maybe there's biofilm, so there's a slightly different or decay rate that happens along the wall. So in WaterCAD and WaterGEMS, you can address that decay rate by entering it in right here. So again, it's like a K value. It is a K value anyway. Okay. A few more areas to take into consideration when you are running a water quality model is what is going on in the tanks themselves. I mentioned earlier the tank initial conditions are pretty important. Well, so is how that water is moving through that tank. Do you have an ideal tank where it's completely mixed and there's a solar panel on top with paddle wheels mixing the tank? Okay, then that would be a completely mixed tank. And that may do its purpose very well. However, if the tank is hydraulically locked out due to high pressure, you may have a really well mixed tank of old water. So sometimes completely mixed tanks in reality may not pan out because of some hydraulic condition in the system. So that's where you would use a hydraulic model like WaterCAD or WaterGEMS to help solve that too. Uh, Depending on the type of tank, it could be plug flow or it could be two compartment. Two compartment, that option at the bottom, you might see that one often if you have a really wide tank where water comes in at one point in the middle of the tank and leaves, but the perimeters of the tank are not really well mixed. So you've got quite a few different combinations here that you can pick from to model the tank that you have or the multiple tanks you have in the water distribution system you're trying to model. So in other words, don't ignore this going in and just assuming it's completely mixed. Might not be the case for you, and it would prevent you from being able to more reliably predict what's going on. And just to compare the differences between these mixing models, CM, the red line, if you can see that on the screen, that is completely mixed. And the completely mixed one you would think would have least variability, and that's the case here, where we're graphing chlorine concentration using these different mixing models. And the last in, first out, the blue line appears to be the one that has the highest variability. That's because there's water in that tank that is more old than the other water molecules that just came in. So there's a lot of variability in that tank at different times of the day. The concentration changes quite a bit. So don't neglect, the point here is don't neglect the initial conditions or the tank mixing model. Okay, steps to running water quality modeling in WaterGEMS. So this is what I'm going to get in and demonstrate for you. You need to start out with calibrated extended period simulation. EPS means extended period simulation. If you don't start off with a calibrated model in the first place, you've already then made quite a few assumptions that may or may not be valid. So calibrate the EPS model as an opportunity to validate your data, your C factors, your demands, your pump controls, your pump curves, your everything hydraulically before you get into water quality modeling. Get into water quality modeling, set up the calculation option, again where you tell it what type of run you're about to do, constituent, trace, or age. Set up the constituent reaction rates. Go determine what those are. Pick the constituent in the alternative. Set up the representative scenario to use that alternative. Set any initial conditions, concentrations in the tank, your mixing model. Press compute, and then review the results. It may take some time to confirm some of these pieces, some of the constituent rates or the tank mixing model, but that's what's necessary to ensure that you have high confidence in your water quality model. All right, today we're going to start off with just a model that I've already got set up. We've got a reservoir and we've got two tanks, so we're not going to deal with too much complexity here. We've got another reservoir at the bottom with a pump, so we've got two different water sources, and we've got 2 tanks. Think of this as more of a skeletonized model, as a simplified model with a little bit less distribution system piping. I wanted you to be able to see everything all at once on the screen here. So, okay. So what I'm going to do is I'm going to go in to my scenarios, and just very quickly I'm going to do what's called a batch run. This will allow me to run everything, run all of the scenarios all at once. So maybe you've got 10 of these, maybe you've got more. Batch run just runs them all very quickly. And again, we're starting with a model that's been calibrated, and it's an extended period simulation model. So we're going to look at the chlorine scenario that's set up. So the very first thing I said earlier that you would do is you would go into calculation options. I'll show you the calculation options here. You would select constituent because we're interested in chlorine, so it's some type of constituent. So select and pick chlorine. And you can then say how long you want this model to run. In this case, it's 288 hours. The hydraulic time step is 1. If you have a really small system, you might reduce the time step because you might be missing some things happening at a greater time step. But generally, for water quality modeling, 1 hour works. All right. And then the other thing that you'll need to go into, again, I'll share this very quickly. This is the WaterGEMS Connect edition, so it might be a little bit different to you from the V8i edition, and developers have done a nice thing and given you and product managers have done a nice thing giving you a search bar. So if you know what you're looking for, but you're not quite sure where it went, you can always use the search bar over here. And I know I want a constituent, so I'll start typing it in, and it'll give you the path, and of course you can click on it as well. So components, water quality, constituents. And we care about the chlorine. So again, I've already set this up just for the ease of the SIG here. But there's our reaction rate that we derive from our bottle test. It's a first order decay rate, negative because it's a decay, but first order means it's an exponential rate. And we are considering today reaction rate at the wall. So we've got first order decay at the wall and some decay rate. So the effort has already been put in the lab to determine and confirm what that K value is. Then it's a simple step of entering that value into the software. So once you have that constituent set up, you would go to alternatives. And I've already got an alternative set up, and it's a simple matter of selecting the constituent that you put into that library. So you'd select that constituent in the alternative. And just as you always would do in your scenario, you would use your scenario to point to the appropriate alternatives. So here we'll see the calculation option for 288 hours. And then the constituent alternative that we selected, that chlorine plus wall constituent. So that is it's fairly straightforward actually to set up that analysis. And again, I can press compute and run it. But we would probably like to see a little bit more. So personally, I like to go look at the color coding. So let me add some color coding here just to start seeing a good picture. So I'll go to color coding. I'll click on this flyout, and we're interested in the water quality results here. So water quality, concentration. I'll do a quick range for just ease here. I'll use the ramping, and I'll be nice and make it darker green so everybody can see that a little bit better. Okay, press apply. I'm sorry, I meant to pick color and size. The reason I want to come back and pick color and size is because it'll make things be more pronounced. Okay, now we have a time browser, and this is the other benefit of running an extended period simulation and a water quality model, is you can press play on this time browser window. So it's called Times, and you go double click on it, open it up, and you'll have a time browser. And once I start it and I press play, it's now looking at all of the results that it collected for each of those time steps, that 1 hour time step. And you can see colors are changing now, so that means some value is something in the model. So at the very least, now we can see that. We probably need to see a little bit more detail. Uh, we could always go to flex tables and look at our chlorine concentration. I'll have to add that here. Let me add it real quick. I'll move it up to the top. Okay, so we can see our chlorine concentration. I'm going to move it off to the side here just to get the screen set up for us. So Flex Tables is the database, if you will, of all of the results and all of the input data. So we'll pop that up, and also I'd really like to see, say, water quality on top of the pipe. And I want to add annotation. So I'll right-click on the pipe in Element Symbology, go to Annotation, and I'll select Water Quality Results, Calculated Concentration. I'll press OK. Give it a quick offset to move the text. Okay, so now we can see the values of the concentrations. And maybe one step further, I want to see what the values are in the tanks themselves. So I'll right-click on tanks, go to Annotation, Results, Water Quality, Concentration Calculated, and press Apply. So now I can see my values in the tanks there too. Now, I have flex tables up, I've got annotation, but with the power of that time browser, I can press play again, and now all of these values are going to be changing. All of the color coding is going to be changing. If you remember, the reservoir can also have concentration. It looks like the concentration in that reservoir is 1 milligram per liter, and it's unchanged. It's coming from the treatment plant, perhaps, and that's what the value is. But as it goes out into the distribution system, you can see how it changes. The concentration is affected by the tanks. It's affected by that K value and the tank mixing models that we selected. So flex table data is changing over here. Color coding, annotation, it's all changing relative to each time step. All right. And we could also be adding in some color coding for pressure on the junctions if we wanted, or something like that as well. So that's the quick run through for water quality modeling with chlorine. Now I'm going to switch to I'll switch to water age, and let me turn off a color code here. And is there so the question, is there a rule of thumb for decay rate? It would be nice if there was, but every system and every water system is unique. The chemical background signatures, the condition of the pipes, the type of disinfectant used, all of those combinations, and how water sources mix and blend, the configuration of the tanks, all of these variables change across the system. But what you're really interested in for the decay rate is what happens in the bulk of the water. So that's a bottle test analysis that just would not yield the same result system over system. It's always going to be different. Now, the wall reaction rate, that's a harder one to get to, and it ends up being more of a calibration number. Okay, so let me get into water age. So I'm going to run the water age model, compute the results, and let me close this for a moment. turn off concentration since we're not looking at concentration. But we're looking at water age color coding. And I'll probably do some color coding or annotation on the tank too. So let me add that. Age calculated, apply. Okay. So I haven't gone in to show you this yet, so now would probably be a good time to walk you through the tanks. So tank 1, for example, initial age is 72. So you'll see right now it's showing NA everywhere else, but it's is still listing 72 hours. Well, it's listing 72 hours because that's the initial age on the tank. This is also where you would enter the initial concentration. On the chlorine model we did that. Or you can select the tank mixing model. Again, we're assuming optimal case here, and maybe there are paddle wheels, or it's a smaller tank that turns over very frequently because of the hydraulic in and out for that tank. So we're selecting completely mixed. But again, this is where you can select 2 compartment and then what percentage of what compartment is what. So we'll put it back to completely mixed. All right, so we'll use the time browser now to press play. And I didn't show you the color coding because I already had it set up, so let me do that for you real quick. Calculate age, full range, and it looks like red and magenta, blue, that's really old water. We'll summarize it by saying that. So really old water. So anything that's red, magenta, blue, it's going to show up. I'll even add a legend here. Insert legend so we can see everything. Run the time. So there's a blue, there's some reds, and we'll kind of notice that blue and red keep popping up pretty close to the tanks, and this is the effect that tanks have on a system. They kind of create old water because it takes a while to turn over the volume of water in that large tank. So this is some of the benefits that you get to see by running a water quality model is predicting where old water is, what the decay rate is, or what the chlorine value is somewhere in the system based on a decay rate. And also look at some nice behavior over time. If we wanted to, we could also graph concentrations over time leaving a tank or something like that. So there's lots of different ways to express the data. And maybe I'll add that real quick just by right-clicking on something, graph, and results, water quality, age. So we'll do a quick graph. And this is a graph of our water age over time. So as we saw everything else changing, we can press play and see at what time step what that value is. You can click on the data tab and look at this very exact data. But basically, the tank age changes over time. So we're able to see it in a graph on the tank. We're able to see it in color coding. You can see it in annotation. You can see it in the flex tables. So lots of different ways to slice the data to look at it to see the picture that you're trying to see. Okay. A lot of things to consider. And again, I'll say we were just skimming along the surface because of time here, and I wanted to show you how to do this. But generally in a class, one of our distance learning classes, we go into a lot more detail with the water quality model, how to do this, how to set it up. So I'd encourage you to consider attending one of those. But if not, again, there's some great sources out there. And DG, your question there, is there a way to filter out and eliminate dead-end mains in water age results? Well, dead-end mains are indeed a problem when it comes to water modeling and water quality because, well, do have older age, the lower residuals. Now, if there are some pipes in your system that you don't want to model, say pump station, or there's some pipes that you just want to lighten the load on your color coding, you can always go into color coding and use a selection set. So selection set is you selected your a set of pipes, highlighted them, right-click, selection set, and that becomes then something that you can pick from this drop-down menu. And then it would only be color coding the elements that you wanted it to color code. Um, you might not want to avoid color coding dead end lines because those could be problem areas and areas that you really may want to pay attention to. Unless there's no connections there or something, but even then it's still connected to the distribution system and could potentially uh, have some biofilm growth or something, or an area where you might need to go flush. But again, if you're just trying to for graphically to display something, you can use selection sets and not select those certain pipes. If you it sounds like you're trying to reset the age to 0 at a tank. So I mean, you could go in and say it's 0 if you're trying to use that as a surrogate to the chlorine levels. But again, then you may be modeling age instead of chlorine. So if you're trying to actually model chlorine, you would then put in what the actual chlorine dosage is if it's near the pump station or something. You would actually enter in that initial concentration. But again, on a tank, I guess maybe just trying to answer it right now, you can set the initial uh, age of a tank to 0 at the start of a run, and age could be 0. In this case, you could enter in 0, but chlorine concentration could still be 1.